All right, in Chapter 6, we're going to talk about how to gather useful data for examining relationships. So first, there are two different kinds of research studies, and you have to be able to distinguish between them. The first one is an observational study, in which researchers just observe or question participants about opinions or outcomes. So that's an observational. So nothing is manipulated, nobody's given a drug, they just ask you what you've done or watch what you do. In experimental studies, researchers manipulate something and measure the effect of manipulation on some outcome of interest. So in experimental and in a randomized experiment, people are assigned to groups randomly. So, anyhow, you can think of things like drug trials where people are randomly assigned to either get the drug or get a placebo. So the first thing we'll do is just see if we can distinguish between these two kinds of studies. So in each situation, indicate whether you think an observational study or randomized experiment would be used. Explain each case. So a teacher wants to compare the grade point averages of female students who are in sororities to the grade point averages of female students who are not. So the question you ask yourself is, were students randomly assigned to be in a sorority or not? And the answer is no. People choose themselves to be in sororities. So this is observational. And the reason is that women are not randomly assigned to be in a sorority or not. A doctor wants to compare the effectiveness of two allergy medicines, so probably going to use a randomized experiment. Where you would divide your sample into 2 or possibly 3. You could use a placebo drug, into 3 groups and give each group drug A, drug B, or placebo. A social psychologist wants to determine whether restaurant servers will get better tips if they introduce themselves by name to the people they serve. So you probably don't want to let people choose themselves if they're going to say their name, because those people might just be more outgoing and might get better tips for that reason. So in this case, I think it probably would be fine to do a randomized experiment. So divide the servers into groups and have half introduce themselves and the others don't. A child psychologist wants to find whether there is an association between the amount of television 6-year-old children watch and how often they bully other children in school. So it's probably the case that the psychologist cannot make people watch a certain amount of TV because they don't have that much control. So this is probably going to be observational. So observational, the researcher probably cannot determine how much TV is watched. So this is a bit of a review, but remember that in a study, it's often thought that the explanatory variable, also known as the independent variable, may explain or cause a difference in the response variable, also known as the dependent variable. And recall that a confounding variable is a variable that is not the main concern of the study, but may be partially responsible for the observed results. So remember that a confounding variable affects the response and is related to the explanatory. For each of the following situations, explain how the given confounding variable meets this criteria. So it affects the response and is related to the explanatory. So the response variable is math skills of children aged 6 to 12, and the explanatory variable is shoe size. Okay, the confounding variable is age. So age affects the response. Yes, age affects math skills. So age definitely affects math skills. And also it's related to the explanatory. So is age related to shoe size? Yes, and age is related to shoe size. And the thing is, what's going to happen here, if you're looking at math skills related to shoe size, it's going to look like big shoe size implies better math skills. At least when you're looking at children ages 6 to 12. Because obviously, as kids get older, they learn more math and their feet also get bigger. But it isn't like if you have big feet, you're better at math than others. But if you can fill in this part, the confounding variable affects the response, is related to the explanatory, then you know it's confounding. So the response variable is number of missing or decayed teeth. The explanatory variable is the amount of past exposure to lead. So it probably will be the case that exposure, I spelled that wrong. Exposure to lead will look like then it's going to be an increase of missing teeth. But a confounding variable will be the number of visits to the dentist the child has in 8 years. So first of all, is that confounding variable affect the response? So does the number of visits to the dentist affect missing teeth? Yes. So the number of visits to the dentist definitely affects decay, missing teeth. And is it related to lead exposure? It is number of visits related to lead exposure. And I would say yes, because people who tend to be exposed to lead tend to also be not very wealthy, and as a result, they probably can't go to the dentist. So because of lack of wealth, I think that's true. So if you're going to design an experiment, let's talk about how you're going to do it well. So an experiment measures the effects of manipulating the environment of the participants in some way. And in a randomized experiment, participants are randomly assigned to either a treatment group or a control group. And a control group is one in which no active treatment is used. So if you were comparing diets, you might have a group where you say, well, don't diet. We'll just provide you with counseling and something, but we're not going to actually put you on a specific diet. With drugs, the control group often receives something called a placebo, which is a sugar pill or a pill that has no effect, or should have no effect at least. So the principle that a single experiment really provides sufficient evidence, and it's important to repeat the experiment again and again, that independent researchers verify the results. This is called replication in science. And an experiment in which either the participants or the researcher does not know which treatment they have been assigned. So the kicker is one person does not know. That's called single blind. And an experiment in which neither the researcher nor participant know who had which treatment, that's called double blind. So something called the matched pair design is where individuals are first matched on important characteristics, and then each member of a pair receives different treatment. So, for example, people might be matched on age. And that could account for the fact that age could be a potential confounding variable. And then the last one is called block design. So experimental units are first divided into homogeneous groups called blocks and then assigned treatment. Suppose we want to determine whether people who want to lose weight would lose weight more in 3 months by dieting or by exercising. 60 people have volunteered to participate and briefly describe how a randomized experiment could be done in this situation. So nothing special, no control, just a randomized experiment. So take your 60 people and divide them into 2 groups of 30. So divide the group of 60 into 2 groups of 30. Randomly assign diet to one group. And exercise to the other. And then just proceed with your experiment and examine the results. In a later chapter, we'll look at how to look at the data from an experiment like this. You'd be able to suppose you know that the average weight loss in the diet group was 10 pounds and the exercise group was 5 with certain standard deviations. We'll be able to discuss, are those results actually different or is it just due to chance? So 20 students agreed to participate in a study on colds, and 10 were randomly assigned to receive vitamin C, and the remaining 10 randomly received a tablet that looked and tasted like vitamin C but only contained sugar and flavoring. The students did not know whether they were taking vitamin C or not, but the investigators did. The students were then followed for 2 months to see who came down with the cold and who didn't. Explain whether each of the following terms applies to this randomized experiment. So, placebo, yes or no? And the answer is yes. There was a fake pill, or sugar pill. Single blind. So the answer is yes. The students did not know. What pill they had. Is it double blind? So to be double blind, the students and the researchers both must be in the dark about who has what. And the answer is no, because the researchers knew who received which pill. And then matched pairs. No, there was no mention of matching people based on various characteristics. Repeated measures, where people measured more than once, like was their cold incidence measured? Nope, it was just at the end of 2 months, see if they had a cold. So no. And replication, well, sort of yes, your book says yes, but I would take either one with this. There were 10 students in each group, so the experiment was applied to more than one person. Although in my mind, I really view replication as the experiment was done again or reproduced. So 20 volunteers aged 40 to 65 will participate in an experiment to compare 2 methods of memorizing information. The age variation in the participants concerns the researchers because memorization skills decrease with age. So for this reason, you want to try to control for that age variable, and matched pair design is a good candidate. So how you perform a matched pair design is you match participants by age. So form pairs of participants by age. In other words, members of a pair must have similar ages. And then within your pairs, randomly decide that assign someone to each of those methods. So now randomly assign each member of a pair to use a different method. And explain why a matched pair design is a good idea in this situation, as in better than just a random sample. And the reason is that the age will affect memorization. And if you have people of similar ages, age is no longer a factor. So this design is a good idea because we want to control for the association between memory and age. So, designing a good observational study. So, that good, I should put good in quotes, because observational studies aren't often good enough to use to draw conclusions, but sometimes you have to do them. For example, with smoking, it's never been proven that smoking causes lung cancer because we've never taken people, put them in two groups, and randomly assigned one group to smoke and one group not to, because it's not ethical to do that. And that was an argument that the tobacco industry used for a long time to justify and say that no, smoking doesn't cause lung cancer. You haven't proved it yet. So anyhow, moving on to different terms about observational studies. So in a retrospective study, data are from the past. And in a prospective study, the researchers follow participants into the future and they record relevant events and variables. And in a case control study, the researchers compare participants who have a particular attribute or condition to those who don't. So a teacher wants to determine how class attendance during the term affects grades on the final exam. So explain how data would be collected in a prospective study. So in this case, you sort of follow people into the future. So I think you take attendance as the semester progresses and then look at grades at the end of the term. So take attendance as the semester progresses, and then look at the grades at the end of term. So you decide in advance that you're going to do attendance, and then you do attendance. In a retrospective study, you wouldn't actually have any data on attendance, so what you'd have to do is ask students. So ask students about their attendance and compare that to exam scores. Okay, so both of these methods have their drawbacks, and that's what the next question will address. So refer to parts A and B and give one disadvantage for each method of collecting data in the situation. So for A, the prospective study, when you take attendance, I've definitely observed this in my classes, you get better attendance, as in people just tend to come more. That's not a bad thing, but by even taking attendance, you affect the behavior of attendance. So some problem here is that students may change their behavior if they know attendance is being taken. An obvious problem with B, as we described it, if we're asking students about their attendance, the big problem is they may not remember accurately. So students may not accurately remember how many classes they missed. And I think it's probably fair to say that you would probably give an underestimate. They would probably give an underestimate. So students whose undergraduate major was economics were followed for 10 years after graduation to study the number of different jobs they took. Explain whether each of the following terms applies to this observational study. So is it prospective? And the answer is yes, because they were chosen and then followed. So yes, students were selected and then followed into the future. Okay, how about retrospective? And the answer, no. If it was a retrospective study, you would have talked to them after 10 years and then asked them about their jobs. So the answer is no. They were not, say, asked about past jobs. I mean, they were asked about past jobs at 10 years, but it was over the course of those 10 years, not just after 10 years they were then chosen and asked. And is it case control? Are they compared to anything? And the answer is nope, not mentioned. So they're not compared to a control group. One interesting question is how might that happen? And so what you could have done to compare to a control group, you could have also followed a group of random majors. And they could be your control, and then you could compare them to the economics case. Now, observational studies are often really, really hard to do well, and there are tons of examples of observational studies being done badly. And if there's one thing I want to hammer home in this class is that you should take the results of observational studies with a grain of salt, because there's often so much stuff going on. So one problem is that confounding variables and the implication of causation in these studies. So you absolutely cannot conclude cause and effect from observational studies. I think one of the only successful cases of that is probably smoking. And you really can only conclude cause and effect from experiments, where people are randomly assigned to a group and treatments applied to those groups. Also, don't try to extend your results inappropriately. The data can only be used to make inferences about a larger group if the data is a representative sample. You can't use college students to generalize about everybody over the age of 18. So there's another type of variable that affects the magnitude of what you see. This is called an interacting variable. And a variable is interacting if it affects the magnitude, which is another fancy way of saying the strength of a relationship between your explanatory and the response. And the interaction is said to be between the two explanatory variables. So those alone. So for example, does a nicotine patch increase success when attempting to quit smoking? So there was a study done, and 46% of the participants using the nicotine patch had quit successfully, and just 20% of the control group had done so. So it looked like a pretty good difference. Now, a possible interacting variable was the presence of another smoker in the home. And when broken into two groups, the success rate for the group with no additional smoker was 58% versus that 20 in the placebo. With another smoker in the home, it was just 38 versus 20. And you see how when you separate out the other explanatory variable, which is smoker in the house, the 46%, the magnitude or the size is different in those two groups. And let's talk briefly about why this is not different than a confounding variable. So remember that a confounding variable So confounding variable is related to the explanatory. And affects response. Okay, so is the presence of a smoker in the home related to the explanatory variable, which is the application of a nicotine patch? And so that is no. So this part of that is not related. That just affects the response. So it doesn't meet both criteria. That's the reason. It's a really subtle difference, and it's not the most important thing. But when you're trying to determine if those two things are different, ask yourself that question: can you do the related to explanatory affecting response thing? If so, it's confounding. If you have something about magnitude or how strongly the relationship is displayed between two subgroups, that's interacting variables. Now, another thing that can happen is something called the Hawthorne and experimenter effects. It's a phenomena that occurs when participants in an experiment just respond differently than they normally would just because they're in an experiment. So, for example, if you have a diet and exercise study, people may just behave better because they're in that study. And in that exercise study, people might eat better just because they're part of this study. Also, using the past as a source of data really is a problem. So, especially when people are just surveyed about past behaviors, you cannot rely on memory to really be accurate. So, retrospective studies should be taken with a grain of salt. Read things like this really carefully and then ask yourself if the results are worth a grain of salt or not. So an article in Science magazine discussed a study comparing the health of 6,000 vegetarians and a similar number of their friends, and it probably should say who are not vegetarian. And the vegetarians had a 28% lower death rate from heart attacks and a 39% lower death rate from cancer, even after the researchers accounted for the differences in smoking weight and social classes. So first of all, is this an observational study or randomized experiment? And so the answer is that it's observational. And people were observed not randomly assigned to a specific diet. So on the basis of this information, can we conclude that a vegetarian diet causes lower death rates from heart attack and cancer? I mean, they do have rates that are quite a bit lower, but the answer is still no. So no, it's only an association. So give an example of a potential confounding variable in this situation and explain what it means to say that it's confounding. So the amount of exercise. We could have sugar consumption, vegetable consumption. All right, this is a confounding variable because all of these three things listed, that is, are related to your explanatory variable, which is diet, and they can affect the response. Which is cancer and heart attack. So you just don't know. They did try to control for some of them, like smoking, weight, and social class. But still, things like exercise might be related to vegetarianism and could also affect the response variable. A retrospective study of 517 veterans who never smoked was done to determine whether there was an association between lung disease and exposure to workplace gases, dust, and fumes. In this study, subjects were asked whether or not they remembered being exposed to gases, dust, or fumes in the workplace, and a concern expressed by the investigators was that patients who have histories of lung disease may be more likely to recall a history of exposure, whether accurate or not, than subjects in good health. So discuss whether each of the following is likely to be a problem in this survey. So relying on memory, and the answer is yes. It's unlikely that participants will remember how much they were exposed to. How about confounding variables? Yes, this is always a problem with observational studies. However, they did try to control for smoking because they said veterans who never smoked, because that would be a potentially big confounding variable. Okay. And the Hawthorne effect, remember that's the effect where participants respond differently because they're in an experiment, and the answer is, in this case, no, because this wasn't an experiment.